Testing 1 2 3.
Testing 1
Mela, bonġu prattikament li ħannamlu l-lum hija ħanduru xi mechanisms li għandna tal-amines. Prattikament ħanistenna 5 minuti oħra biex kull għandi jidħol ikun daħal. Jien iskuża ruħi daqsxejn magħkom, jiena ftit ma niflaħx. M'għandix il-coronavirus imma għandi bronchitis qawwi, so hopefully ikun se nagħmel il-lezzjoni minn problemi ta' xejn. Użaw il-live chat. Jiġifieri jekk intom ma tifhmux xi ħaġa, toqgħodux tidejqu istaqsu fuq il-live chat. Naf li dan huwa metodu mhux daqshekk normali, mhux daqshekk komuni, qed nuża il-live stream ta' YouTube ħalli intom tkunu tistgħu tparlaw mill-ewwel miegħi. Ma taraw il-video u nitkellmu wara. Ma xtaqx nuża Zoom jew Skype għax onestament ma nafx kemm il-computer tiegħi kapaċi jiflaħ għal dawk l-streams kollha. Issa, kif intom? Nispera kollet nisabu sew, kollet nisabu tajjeb. Ikolkom bżonn xi ħaġa dediqqu xejn tajduli, jiena qiegħed hawnhekk biex ngħinkom. Naħseb smajtu li l-Università ħad tiftaħ mhux qabel is-17 ta' April. Jiġifieri għandna xahar ieħor ma mmorrux l-Università. Naf li suppost hemm l-Easter holidays, imma ħanieħu daqsxejn vantaġġ biex nagħmel lezzjonijiet tal-inqas darba fil-ġimgħa satej. Il-lezzjoni tal-lum ta' tkun daqsxejn qasira għax jiena qed imbagħad biex nitkellem, ma jimpurtax qed naraw. Importanti ħafna li kulħadd iżomm f'moħħu li s-saħħa tiġi l-ewwel, kolkom bżonn xi ħaġa tiddejqu xejn għajduli u nirranġaw. Mela, illum li ħanagħmlu hija li actually ħanduru il-mechanisms li tkellimna fuqhom fl-aħħar lezzjoni. Issa, x'inhu huwa mechanism? Mela ħaġa li rridu nifhmu hija li mechanism huwa il-moviment tal-electrons. L-electrons ħajmorru minn area fejn ħajkollok. Actually, let's say this in English so that everyone can understand. Electrons tend to move from areas of high concentration, so high electron density, to areas of low electron density. Now, normally electrons start from a nucleophile, and inorganic compounds, they tend to attack the most acidic hydrogen. Now, amides are not really truly acidic. Amides are normally considered actually as something slightly basic. But in this case, the amide here is a diamide, meaning you have an amide group and a second amide group. And here you have an acidic proton. This acidic proton is acidic because of what we can consider as a resonance form of the product. So you can see that the product, the negative charge, can be transferred to both oxygens, and that would give an actual stable conformation, making that proton acidic. Once you get the acidic proton out, you end up with a negative charge on the oxygen and an imine. Now, again, this is not a true imine, okay? But the electrons can push from the negative charge and onto the nitrogen. What does that make the nitrogen? It makes the nitrogen nucleophilic. Now, a nucleophilic nitrogen can react with a halogenoalkane. So what happens at this point? At this point, what happens is that you form a secondary amide, a secondary diamide. And here you can actually continue to form the amine. Now, what do we mean by this can form the amine? So this reaction at this point can give one amine and one amine only. So last week we were discussing and we were saying that there were a number of different possibilities where the amine could form the primary, secondary, or tertiary amine. This methodology enables that you get the amine that you require. Once you form the nitrogen-carbon bond, a hydrazine can attack. Now, let's note the arrows. The arrows need to start from a lone pair, again, an area of high electron density, attacking the carbonyl carbon, going through the oxygen, and going to the nitrogen. So we are breaking a bond. What does this form? This forms this compound down here. Again, you have a positive nitrogen and a negative nitrogen. So what happens? The negative nitrogen loses a proton. Sorry, the negative nitrogen accepts a proton from the hydrazine derivative. This is the hydrazine derivative, and this negative nitrogen is giving 2 electrons to the proton, breaking the nitrogen-hydrogen bond. Now, here you've got a cyclization reaction. Again, you have a second nitrogen in the hydrazine. This second nitrogen is possible to act as a nucleophile. So what happens? This second nitrogen reacts with the carbonyl, releasing the amine. Once the amine is released, you can get back the amine and you can get back the diamide. This diamide just needs to lose an NH3. Okay? So this is pretty much your end product. Okay? This can be recycled. So this is the Gabriel synthesis. Where do we use the Gabriel synthesis? The Gabriel synthesis, we use it to make primary, secondary, or tertiary amines. Now, using the organic chemistry portal, you can all actually find a few papers in literature where this is used. I do not expect you to actually read all the papers, so let's make this clear. Here, you want to learn. You want to try new things, you want to actually do something new. Now, going through literature is not always the easiest task, but as long as you can replicate this mechanism and drawing it again on your own, without actually looking at the notes, looking at the book, then you have succeeded in understanding what you need to do. This again is what is going to be expected out of you in the exams. Okay? So as we said in the other mechanism, let's take a look at the mechanism given in the organic chemistry portal. You use a base, you deprotonate the phthalimide. Once you deprotonate the phthalimide, the nitrogen is nucleophilic, which means that it can attack a halogen alkane. That means that you can actually break the bond by using something like hydrazine or an NaOH, and then you can form the amine. Now, the mechanism I've given you and the mechanism I expect you to know is a bit more detailed than the one present here. Please do know how the cleave takes place. Okay? So this step here is actually very, very, very important. Now, what is required out of students? So, what I want you to do for now, and I understand how difficult this may seem, okay? But I want you as students to try and take 5 minutes to draw the mechanism on how to prepare ethyl methyl amine. Okay? So I want you to try and take a couple of minutes to try and prepare ethyl methyl amine. Or to make it easier, do propylamine, okay? So I will leave the mechanism here so we can try and draw a mechanism to make propylamine starting from thalidomide. Again, if you have problems, please don't hesitate to ask during the live chat. Okay? I am taking a note at what you're saying, if anything, so that I can help you out the best possible way. I know it's not the best method to teach chemistry, but at least we can try and do our best. Now, the second mechanism that I want to look, and this is not actually truly a mechanism here, is the reductive amination. So, what is reductive amination? When we react an amine with a carbonyl, we produce an amine. So, the lone pairs on the nitrogen react with the carbon to produce an alcohol and a secondary amine. Now, this would then lose water to produce the amine. Once the amine is formed, this can then be reduced to form the new amine that you require. Now, reductive amination is possibly one of the easiest ways how to prepare amines. But you can only do this for secondary or tertiary amines. You cannot do this for primary amines. Why is this so? Because you require to lose the protons. Again, tertiary amines might be a bit of a problem here, but it should be possible. So, for reductive amination, what do we have? We have an amine reacting with a carbonyl, forming the amine. This is done in a number of different steps, where you first react with the carbonyl to produce an amine and an alcohol, then it loses water to form the amine, then the amine can be reduced. It can be reduced with either NaBH4, NaBH3CN. If you really want to, it can also be reduced with ILH4. All the reactions will work, reactions will require different conditions, mainly the conditions will be the different solvents. Now, during A-level times, we used to tell students, if you want to reduce a carbon, the only way to do it, or one of the only ways to do it, is to use the Hofmann degradation. This is, in my opinion, one of the most important reactions that you've done at A-level, because you could go from having 4 carbons to having 3 carbons. Now, what does it mean to have removal of carbon? It means that you're breaking a carbon-carbon bond, which up to now has been quite difficult. And how can it be done? Our conditions at A-level were Br2 and NaOH and reflux. So, this is also known as Hofmann Rearrangement. Rearrangement because you are moving the structure around, actually releasing CO2. So, what's happening? What's happening is this. First, using a base, you are going to attack an acidic hydrogen. Again, the most acidic hydrogen will be the amide hydrogen. Remember, here we're not saying it is acidic. Here we are saying it is the most acidic hydrogen. Okay? Now, once you do that, you form a negatively charged nitrogen. This is highly, highly reactive. And in fact, it can react as a nucleophile with bromine to form this compound down here. This intermediate is actually a little bit more reactive than the actual starting material. Okay? The bromine pulls electrons a little bit. It's not highly electronegative, but it's electronegative enough to make it a bit more reactive, which means that this hydrogen here will be easier to lose. Once you do that, the process repeats, so you form a negatively charged nitrogen, and then you can actually lose the nitrogen-bromine bond. Once you break the nitrogen-bromine bond, you have 2 lone pairs on this nitrogen. There are no charges, so this nitrogen has the 5 electrons. It's 1, 2, 3, 4, and one of the electrons in the bond. But again, this will be highly reactive. It has 2 lone pairs. Where have we ever seen nitrogen with 2 lone pairs? Pretty much never. This is going to be highly, highly reactive. Okay? So what happens? There will be a rearrangement. The ethyl group in this case will move and attack the nitrogen. This forms a positive carbon, because the electron is being taken from the carbon down here, and the electron is added on the nitrogen. So it forms a positive carbon and a negative nitrogen. But all of these atoms here, no, actually no. So this carbon here has only 6 electrons. It doesn't satisfy its octet rule. But here you can have the rearrangement. So the nitrogen gives the electrons to the carbon, forming a double bond. All of the electrons here now, all of the atoms have 8 electrons, meaning that this compound would actually be quite stable. But this carbon can then be attacked by a base. Once it's attacked by a base, it will still have the double bond with the nitrogen, but it will have 2 single bonds with the oxygen. Here, what will happen? Here you will end up having the possibility of losing carbon dioxide. This is the starting place of how to lose a carbon dioxide. How does it happen? The oxygen gives a pair of electrons onto the carbon, which loses a pair of electrons from the double bond with the nitrogen. This ends up producing what? This ends up producing a negatively charged nitrogen, and there is a hydrogen, a slight acidic hydrogen, because this is a carboxylic acid here next to it. So of course the nitrogen the negatively charged nitrogen will react with the hydrogen, giving the electrons on the oxygen. The last step would then be to produce CO2 and release the amine. Again, it's not an amine yet because this nitrogen has too many electrons. So what it will do is that it will react with water, releasing the hydroxide and the amine. So we can say that the hydroxide used in this reaction, you are actually regenerating it again. That's why the hydroxide is a catalyst. Important to note, the bromine is also generated, but this is a bromide ion now. This is not the bromine molecule, okay? So you lose bromide and not bromine. Now, this is a very neat mechanism where you can get pretty much any amine you want from an amide, but you first need to generate the amide. So similar to the reductive amination, where we started with an amine and the carbonyl, and we formed the amine of our choice, you can here form an amide, and from the amide you can start and you can generate the amine of your choice. Now, again, try and write, take 5 to 10 minutes. Now this is a long mechanism, but it's important for you guys to be able to practice. It's important for you guys to be able to actually understand what you're doing, and if you have problems, ask. You can either ask now, you can ask later. I will write my email address on the live chat later on, but please do not be afraid to ask. These mechanisms are actually very, very important. So take 5 to 10 minutes to actually try and draw the preparation of propylamine. Okay? Yes, Jake, it would be. It all depends on what your starting structure is, starting molecule is. So if your starting molecule is a tertiary amide, okay, and amide, then of course your product would be a tertiary amine. I don't have an example with me for how to form a tertiary amine, but I can look it up and give you a few reactions. Are you all following what we're doing at the moment? How are you all understanding these mechanisms? Again, it's quite heavy. I will be sending you this document so you can actually have everything yourselves. I can actually send the document now. Now, how is this sound looking? Because I've had some feedback that there might be some relays and you know everything. I am taking a few minutes break after this mechanism so we can reread it. And apart from that, my voice is also not the best. My throat is hurting a bit, so I'm trying to save myself. But please do tell me if you can't understand something with regards to my microphone and my mics. Okay? So, the Beckmann rearrangement. I do believe that this you've actually done in the lab. For polyamine, you have to start from the butanamide. But of course, you are removing a C double bond O, which means that you need to start from the 4 carbon, which would be the butanamide. Welcome. Now, the Beckmann rearrangement. You should all have done this in the lab. Okay? So by now you probably are all professionals in this mechanism. Now, what is this mechanism? The starting material is probably not something you are very common. Okay? It's a hydroxylamine. Hydroxylamine, when you have NH2OH, it's an amine because you have a C double bond N. So the first thing is that if you add a proton, what happens? If you add a proton, you end up having an OH2 and a negative charge. This allows to lose water. So water is not normally a good, it's quite a good leaving group. OH minus is not a good leaving group. So if you want to lose an OH, you first have to do it by protonation of that oxygen to produce NO positive. And then water can be lost. If water can be lost, then you can actually have a concerted process. A concerted process is a process where the electrons are being moved at the same time. And you end up changing the structure. So you go from having a carbon-carbon bond to having carbon triple bond N and a nitrogen carbon bond, as you can see here. Okay? Now, at this point, you can then add water, and the water will now react with the positively charged carbon. So we have two resonance forms. The resonance forms are actually both important because one of them is shows the stability of the compound. The other one, so they are here, you have 8 electrons on each. The second one shows that the carbon is slightly positive, which means that it can react with water. When it reacts with water, it actually forms a hydroxyl ion, which can then lose hydrogen or a proton. Again, this was the catalyst to then give the final product. Now, this is a rearrangement. We're not really doing anything major here, but you have changed the skeleton of your compound without losing functionality. Not losing functionality is very important. Okay? Because functionality is good. This is actually an amide now. Okay? So you're forming a secondary amide. So starting from the hydroxylamine, you can finish up with a secondary amine, first do the Beckmann rearrangement, and then doing the Hofmann rearrangement, or as you probably know it better, the Hofmann degradation. Now, I'm not going to tell you this is what I will be asking you in the exam, but I would love to be able to actually tell you and give you more than one mechanism in conjunction with each other. What does that mean? That I will tell you the structure first follows the Beckmann rearrangement, then you have the Hofmann rearrangement, draw the mechanisms. Because that way I would ensure that you didn't just study and learn the mechanisms by heart, which is probably the easiest thing to do, but you actually tried to understand and tried to work everything as it should be. Okay? Remember, mechanisms are a tool that will help you get better in chemistry. Now, how were you in stereochemistry? Honestly, these were never my favorites, but they are very, very important. Stereochemistry is very, very important. Note, now you can see this as the product, but note that depending on where the groups are, you'll get a different product. So here, let's call them cis and trans. If they are on the same side, they will be cis. If they are on opposite sides, they will be trans. Okay? So, what is happening here? For cope elimination, you have a quaternary salt or a tertiary amine that is oxidized, which then loses the quaternary amine group. So once you have an amine, you can oxidize it. It has to be a tertiary amine. Once you oxidize it, then this can do 2 plus 2 plus 2 movement of electrons. The electrons can move, forming a hydroxide, a double bond, and a secondary amine. Again, this is possibly very useful because then the hydroxylamine, you can remove the hydroxy group. So, this depends on where the groups are. Not all tertiary amines, even if there's a hydrogen available, can actually undergo cope elimination. Cope elimination requires syn periplanar elimination. What does this mean? This means that the carbon nitrogen and the carbon hydrogen have to be on the same plane. Syn means same, periplanar would be the plane. So it requires them to be on the same plane. If it's not on the same plane, this will not work. Okay? Now, here you've got the nitrogen and the hydrogen being on different sides. There will be no reaction. Okay? And this is the most stable conformation. You can tell me, but you can rotate the bond here. This reaction will not work. Okay? Because the bulky groups would be close to each other. Again, cope elimination. Cope elimination is not the most difficult, okay, but it's something that is not commonly used because the product itself is not going to be the most useful product. For me, for now, the Beckmann rearrangement followed by Hofmann degradation would be probably the most useful. For people who are rewinding, or it's not a problem, I will leave this video online for the foreseeable future. So if you want to rewind, if you want to see what I'm saying, you can do this whenever you want. Now, can the anti-addition happen if there are no bulky groups in group elimination? I would personally need to check. It has to be syn. So if the bonds can rotate and they can be in the syn position, then there is no reason why it shouldn't happen. Okay? But I would need to confirm that. In this position, you can see that the bulky groups would actually interfere. Okay? Here you have a phenyl and hydrogen, which is the most energy favorable. Here you don't. Remember, here we are looking at energy favorable reactions. Doesn't mean they don't happen, but they can happen very slowly. And the problem when something happens very slowly is that there is a good possibility that other reactions can happen in the meantime. Okay? So the most favorable reaction is going to be the best reaction for you. Now, we have a few more mechanisms, so I would like to finish these today, but I'm going to give you plenty of time to actually go revise. I will be sending you later on this week some questions that I think are relatable to these mechanisms, where you can actually try them out. If you want me to correct them or to check them for you, please don't hesitate to send them as an email. And of course, there is always the possibility where I can send you the answers directly to you as well. For me, these mechanisms are very important. Okay, we're going relatively quickly because you can always rewind and check what I'm doing. Because normally these mechanisms in class would have taken 2 to 3 hours because I will be drawing them on the board, I will be giving you time to draw them. But as the situation is, with us not actually seeing each other before the 17th of April at the earliest, then I think it's going to be quite important that you can learn on your own. I do not presume that we'll actually be seeing each other on the 20th of April, which would be the first Monday of the 17th. But that's an assumption. Hopefully everything calms down and we can continue our everyday lives. So, Hofmann exhaustive elimination. So, what is the Hofmann exhaustive elimination? This is an elimination of trimethylamines. Okay? And this proceeds with anti-stereochemistry. Now, what happens here? First and foremost, you need methyl iodide. Why methyl iodide? Because it can react with the amine to form the salt, the quaternary salt. Once you form the quaternary salt, you can heat with silver oxide. The silver oxide facilitates the elimination, where you end up having the alkene. The alkene is anti, okay? It's always trans. So this elimination happens by the hydrogen losing the electrons, forming the double bond, which then gives the electrons to the nitrogen to form the tertiary amine. So again, this is the formation of an amine. Here it has to be a tertiary amine. This cannot be done for anything else. This has to be a tertiary amine. If you start with a primary amine instead of a tertiary one, you possibly end up still methylating more than once because it will be losing the proton. Okay? You have a hydroxide which will actually take in any available protons. So this will form a tertiary amine, but more importantly, it's forming the alkene. So here normally it is the alkene that you are looking for and not the amine as such. Again, you can take a look at the Hofmann Elimination from the organic portal. This website is very, very, very useful. I can't emphasize enough how important this website is going to be for you to become good organic chemists. Okay? Good organic chemists do not just relate on the knowledge of what they learned at school. They can actually go look up mechanisms and be able to read the new mechanisms that they have never ever seen before. Now, before we go into the manic reaction, have you heard anything with regards to university, when it will open, exams, and so on and so forth? Because presumably you might still be a bit in the dark, because I have not received anything from university telling me with regards to the class I'm attending. Okay? It's something where chase them. I'm telling you, chase them. The department especially, so that they stay on top of things. I'm not entirely sure what's gonna happen with respect, first and foremost, to the, what do you call it, with respect to MedSec. So MedSec is going to be probably the big wake-up call that you're going to be needing, whether you're going to have exams or not. If MedSec postpone their exams, that's going to have a domino effect at university as well. But even if you ask me, I can still check with the lecturers, but till now you should be going back to university after the Easter holidays on the 20th of April. With regard to the practicals, I don't think that you will have enough time to finish all the practicals. That means you can either, there are two options that I can see. Either the percent of practicals is not calculated, or else you would have to do the practicals at some point before the September session. Don't worry, I will not let anyone fail the exam because the practicals were not done because of sickness, because of this disease, okay? Thank you, Steve. I don't think it's just in Agra though. To be honest, this is something that is bigger than the chemistry department. Because practicals, a number of departments have practicals. We'll wait and see. But as I told you, from my side, I'm not gonna be pushing for you to do the practicals now and yet. But if you do miss the practicals or the organic practicals, and you don't choose organic dissertation next year, then it might be useful to actually do the practicals next year at some point, just as practice. Not to do the write-up, not to do anything else, but just as practice. But that's my opinion. Okay? So, we'll see. The last mechanism that we're going to be speaking about today is the manic reaction. The manic reaction is a very useful reaction, and it's one where you can get increase in carbon chain. Brilliant. You increase the carbon chain and you can actually keep functional groups, functionality. Now, I make a massive effort on noting that you keep functionality. Why? Because if you change a compound, you change it to whatever you want, but the functionality is lost, therein lie problems, because the reaction has to stop there. But if you keep functionality, then you can continue the reaction, you can continue other methodologies. So, the first step, similar to the reductive amination, is to react the nitrogen with the carbonyl. Once you do that, you end up having a negative oxygen and a positive nitrogen. This can easily be sorted with the oxygen gaining a proton and the nitrogen losing a proton. Okay? Now, this proton can either be gained or lost to the surroundings, or it can be an interdisplacement, okay? So displacement in the same molecule. Sorry, intradisplacement. But there are protons in solution all the time, okay? So it doesn't have to be for this molecule. Once you do that, you have an amine and you have an alcohol. What can happen here? What can happen is that you end up having the hydroxyl group, which can take a proton. This proton makes it easy for the water to be lost, forming an amine. The amine, you can have the positive charge on the nitrogen or the positive charge on the carbon. Again, remember, this is the most stable resonance form because this has 8 electrons on both the carbon and the nitrogen. Whereas here you have 6 electrons for the carbon and 8 on the nitrogen. Once you get to the amine, you can react it with a new carbonyl group. Now, important that this carbonyl group has to be a non-enolizable aldehyde. Apologies. It has to be an enolizable aldehyde, which means that you can form the alkene and the alcohol. So, do you remember tautomerism from A level? This is a tautomerized, okay, structure. The tautomerized form would be this one here, where it loses a proton to form an alkene and an alkoxide. This is an enoxide here. But normally it is this nuclear that is going to be the most important, the most reactive. Now, if we want to react this negative charge here, we don't simply say negative charge to the amine. That is not something that we do. We normally push the electrons from the negative charge on the oxygen to form the carbonyl, and then we do it from the alkene. Why? Because this is more or less stable. Having a negative charge on oxygen is very, very common. Having a negative charge on a carbon, for us, it's not that useful. Then it reacts with the iminium salt, okay, iminium ion that we produced before, to form a new compound. This has increased the carbon chain, and it has also increased the functionality. In my opinion, this resembles the aldol reaction that you've done at A level. Okay? I'm not entirely sure whether you've done the aldol reaction at some point in university. I do believe so. This is very, very similar. But instead of having a made electrophile, you made it yourself. Okay? But This is a way how to increase the carbon chain and actually how to make a very much more complex molecule than your starting materials. In chemistry, when you do a reaction, you normally try to increase the complexity. You don't want to go from a simple to a simple molecule, or even worse, from a complex to a simple molecule. You try to increase complexity, and the product is much more complex than any of the three reactants. You have 1, 2, 3. Okay? Again, I will be giving you a few reactions so that you can work these out. Now, this I'll probably try and do in class. If not, it's not that important. Okay? It's how carbenes react with alkenes and how to form carbenes from the azide salt. From the azosol, sorry. But for now it's not important, it's in the syllabus. I don't really want to do it via chat because it's not the most important reaction that you will ever deal with. Now, back at A level, you had the diazonium salts. Back at A level, you actually had the diazonium salts, and the diazonium salts were actually something that are very, very useful. One of the uses is for benzene reactivities, so benzene derivatives. But another useful thing for diazonium salts is as tests, because they can distinguish between primary, secondary, and tertiary amines. So, the mechanism is the same for the of them, but it just stops at different points. What does it mean? For amines, it ends up having the diazonium salt, okay, which can then react with water to form alcohols, alkenes, or any other thing. But this is the brilliance of this reaction. This reaction is dependent on the number of hydrogens on the nitrogen. If you have 2 hydrogens, it can go to completion. If you have 1 hydrogen, it stops at the nitrose or amine, and if you have no hydrogens left, the reaction just doesn't take place. So, what happens when you react the diazonium salt, when you react the amine with nitric acid, nitric 3 acid, you form the NO plus, and of course the lone pair will react with the N positive nitrogen, forming a nitrogen-nitrogen bond. The positive charge here will be on the nitrogen, but that's not a problem because it can lose a proton to give a stable product. By stable product, I normally mean that all the atoms have obey the octet rule. Okay? Atoms want to have 8 electrons, especially period 2 atoms, and here they all have the 8 electrons. Now, this can tautomerize. So, in reality, this functionality here is very similar to an enol, or a carbonyl that can form the enol. So this tautomerization is the same. There is no difference. The only difference is that instead of having carbons, you have nitrogens. But once you form the hydroxyl group can protonate, and once it protonates, as I said before, water is a good leaving group. So you can then lose the water, forming an N triple bond N. This is the azo group that are the diazonium salt that we know is a good leaving group because it can release nitrogen. Once it releases nitrogen, you form the R+, and from the R+, you can get to the alcohol. So this reaction is a good way how to go from an amine to an alcohol. This is not a preparation for alcohols. This is just a means how to go from amines to alcohols. Okay? Now, secondary amines, you cannot lose the second proton. So once you get to this position, you cannot tautomerize. So you end up with the nitrosoamine. So this releases a gas. Here you end up having a yellow oily liquid. In the tertiary amines, there is no reaction. Not just no reaction, there is also the possibility that this will not even mix with the water. So you have to take note of that. I think, in my opinion, going through the mechanism of what's happening in this reaction gives you a better understanding why primary amines, secondary amines, and tertiary amines give different products when reacted with HNO2, when reacted with nitric acid. Okay? In my opinion, this clarifies a lot of things. Now, I don't want to spend a lot of time on phase transfer catalysts. Mainly because phase transfer catalyst is something that you will probably be doing in different chapters. But a phase transfer catalyst is when you have a catalyst that, depending on what it's carrying, it can either go into the aqueous phase or in the organic phase. So for example, let's say you have an amine. Amines are more soluble in the organic phase. But if in the organic phase it's formed to quaternary salt, so you add a methyl group to it, then that salt will actually be more soluble in the aqueous phase. So you end up transferring a methyl group from the organic phase to the aqueous phase, where it can react. Once it reacts, it releases the amine again, which can continue the cycle. Now, this is very, very useful and a very, very neat use of amines. It doesn't have to be an amine. This can be used with anything that has a lone pair, a nucleophilic lone pair that can form ions and non-ions. It has been used quite often in the past, so to try and actually have different solutions with different reactions going on. I've seen this happen with limonene myself, reduction of limonene. It was actually very, very interesting, but these reactions aren't that common for a reason, because it is quite difficult to get the catalyst to cycle through. Okay? But it is possible. For today, we just passed the hour mark. Now, I think personally we've covered a lot of material, and if I were a student, by this point I would have a massive headache. I would like to stop the lesson here. Now, the video will still be online. If you have any feedback on what I could be using to transmit the live streams, please do tell me. I am not against the use of Skype and Zoom and Pronopto, but I am against students streaming at the same time. What does that mean? It means I don't want you to have cams on, I just want you to be able to discuss with me and tell me what's happening. Because I do believe that if there are 15, 16 people with cameras on in the same group chat, that might be a bit of a problem. Now, do tell me, give me your feedback with regards to today's lesson, what you've understood, what you didn't understand, but more importantly, the clarity of how I explain things. I have a board here, and I can use my board. I also have a camera which I can change between one screen and the other. The reason why I'm not going to be using the board for this lesson at least is because I want you as students to actually draw and rewrite all the mechanisms. Ovviamente, this I will be aiding by giving you a few questions. But I want you to be in a position where you can actually try things out. You can actually use your organic chemistry book, forgot the name to be honest, the Volhard, so that you can actually get a bit more information. Mechanisms aren't that hard as long as you can try and follow the electron densities. If you start the electron densities, then you should be fine. Okay? But please don't hesitate to ask. My email address is this. So if you do need anything, send me an email and I will be able to answer most of your questions on the same day. Yes, sometimes there can be a few delays, but unless if it's something urgent, normally I take a look at my emails on a daily basis and I will be able to assist you further with anything that you may need. Okay? I bid you farewell for the day. If you do need anything, send an email or a message on Facebook. It might be a good idea to actually have a Facebook group, considering what's happening at the moment, so we can keep each other updated with regards to lessons. But other than that, feel free to ask, to message, to WhatsApp, and I'll answer any queries you might have. Thank you, and of course, during these times, stay safe and stay healthy. Welcome.